Good evening, everyone. Today we continue with our topic electricity. So we'll just continue with the topic. We have completed till Ohm's law and we also did some numericals. Now we start the second part of this chapter. Okay, electricity. So in electrical gadgets, we use resistors. Okay, but how are the resistors arranged? That's a good question. So resistors are used in various combination and that is based on Ohm's law. So there are two popular methods of joining the resistors. First is the resistors can be kept in series. Like in this case R1, R2 and R3 are arranged in series combination. Okay. And this is the second connection in which we can see that resistors are kept in parallel connection R1, R2, R3. And in both the cases, the ammeter will be connected in series and the voltmeter will be connected in the parallel connection with respect to the resistors. Okay. Now let's move ahead. Okay, so when the resistors are kept in series and when the resistors are kept in parallel, how do we calculate the total resistance? That's the next challenge. So if the resistors are kept in series R1, R2, R3, we have to join the three resistors having resistance R1, R2 and R3 and that is kept in series. Now we connect them with a 6 volt battery, an ammeter, a plug key and we note the ammeter reading. Ammeter will measure the current. So change the ammeter will measure the current. So change the position of ammeter in between the resistors. The value will remain the same. In a series combination of resistors, the current is same in every part of the circuit or the same current flows through each resistor. Okay. Now we insert a voltmeter across the N, X and Y of the series X and Y of the series combination of three resistors. So note the potential difference V. Now measure the potential difference across the two terminals of the battery and we compare the two values. Now measure the potential difference V1, V2, V3 across the first, second and third resistors separately. Okay. So basically the potential difference, the total potential difference across a combination of resistors will always in series will always be equal to the sum of potential difference across the individual resistors. Okay. Now let's move ahead. Fine. The three resistors can be replaced by an equivalent single resistors of resistance R such that the potential difference and current remains the same. Okay. So basically what happens is, what it's trying to say is that in a resistor, when a resistor is kept in series, total resistance is always their sum R1, R2 and R3. Okay. And in parallel it is 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Let's see one problem. An electric bulb is there whose resistance is 20 ohm and the conductor of 4 ohm resistance are connected to a 6 volt battery. What are we supposed to calculate? We have to calculate the total resistance of the circuit. So as we can see that 4 ohm resistor and the 20 ohm bulb are kept in series. So total resistance will be 20 plus 4, that is 24 ohm. Okay. Then the second we have to find is the current through the circuit. Potential difference we know is 6 volt. Resistance we know is 24 ohm. So R is equal to V by I or I is equal to V by R. 6 by 24. So you will get 0.25 ampere. Okay. Third, the potential difference across the third is the potential difference. Third is the potential difference across the electric lamp and conductor. The potential difference across the electric lamp is R is equal to V by I. So V is equal to IR. So IR. So there will be difference voltage for both because resistance is difference. So potential difference across the electric bulb will be the electric bulb's resistance multiplied with the current. 20 ohm into 0.25 ampere, that is 5 volt. Potential difference across the conductor will be 4 ohm into 0.25 ampere, that is 1 volt. Okay. If the series combination of electrical lamp and conductor is replaced by an equivalent resistor, its resistance will be R is equal to V by I, that is 6 voltage by 0.25 ampere, that is 24 ohm. This is equal to the sum of the two resistance. Okay. Now let's move ahead. Now we make a parallel combination XY of three resistors having resistance R1, R2 and R3 in electric circuit. Connect a voltmeter in parallel with the resistors. Okay. Note the ammeter reading I and the voltmeter reading. Okay. Voltmeter shows the potential difference. Voltmeter shows the potential difference V across the combination. The potential difference across each resistor is also V. This can be checked by connecting the voltmeter across each individual resistor. Okay. Now insert the ammeter in series with the resistor R1. Note the ammeter reading. Similarly measure currents I2, I3 through R2 and R3 respectively. Basically this is just the derivation of the formula on how we want to measure the resistor in parallel. That is 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Okay. In the circuit diagram given below, the resistance R1, R2, R3 have values 5, 10, 30 respectively, which have been connected to battery of 12 volt. Where is the diagram? Calculate the current through each resistor, total current in circuit and total circuit resistance. Okay. R1, R2, R3 are given, potential difference across batteries given. This is also the potential difference across each of the individual resistor. Okay. So the current I1 through R1 will be R is equal to V by I. So I is equal to V by R1. 12 by 5 ohm, that is 2.4. V is constant for all, R is changing every time. Current I2 will be V by R2, 12 by 10, 1.2 ampere. I3 will be V by R3, 12 by 30 is 0.4 ampere. Total current in the circuit is the sum of the three current, I1 plus I2 plus I3. That is your 4 ampere. Total resistance will be 1 by Rp is 1 by R1 plus 1 by R2 plus 1 by R3. Okay. That is simple. 1 by 5 plus 1 by 10 plus 1 by 30. Normal LCM and we solve it. We get resistances in parallel connection is 3 ohm. Okay. Now we have one more problem. This the diagram is there. We have this R1 and R2 are in parallel. R3, R4, R5 are also in parallel. And the values are also given 10 and 40, 30, 20 and 60. And a 12 volt battery is connected to the arrangement. What we have to calculate is the total resistance circuit and the total current flowing in the circuit. See, we can get such questions. Total resistance will be R1 by R2 is in parallel. So 1 by R equivalent will be 1 by R1 plus 1 by R2. In this case. And then here again, these three are in parallel. Again, we have to do the summation of these. We have to calculate the resistance flowing across these three. That is again, they are in parallel. So 1 by 30 plus 1 by 20 plus 1 by 60. So this resistance will be 6 by 60, that is 10 ohm when we reverse it. Same thing here, 1 by 10 plus 1 by 40. So we get 5 by 40, we reverse it because we want R, not 1 by R, we want R. So 40 by 5 is 8. Now total resistance is, since this and these are in series, we will add them. 8 plus 10, 18 ohm. So total resistance is 18 ohm. And how to find the total current flowing? R is V by I, so I is V by R. So V is your 12 volt voltage divided by 18 ohm is your resistance. So you will get I is equal to 0.67 ampere. Okay. Resistance of a system of resistors. So first we will see the disadvantages of a series circuit. Why series circuit is not having complete advantages. What are disadvantages of series circuit? The current is constant throughout the electric circuit, so it is impracticable to connect an electric bulb and an electric heater in series because they need currents of different values. So if one component fails, the circuit is broken and none of the component works. It is very difficult to locate the dead bulb in fairy lights. Okay. Next is advantages of a parallel circuit. It divides the current through the electric gadget. See, it is a parallel, so it is dividing the current across the gadgets. If the total resistance is decreased, this is helpful when each gadget has different resistance and requires different current to operate properly. Now we go ahead. Heating effect of electric current. Now we will understand what are the heating effect of electric current. Okay, a part or source of energy is consumed into doing useful work whenever a current is switched on, like the rotation of fan or something like that. But there is some energy that is always lost as heat. So an electric fan becomes warm if used for a long time. Okay, so we will try to understand the heating effect of electric current. In an electric circuit is purely a resistive. The source energy is dissipated entirely as heat. This is called heating effect of electric current. Okay. Consider a current I flowing through a resistor of resistance R. Let the potential difference across it be V, and T is the time during which a charge Q flows across. Okay. Okay. The work done in moving the charge Q through a potential difference V is V into Q. Therefore, the source must supply energy equal to V into Q in time t. Hence, the power input to circuit by source is P is equal to V by QT or V into I. Okay. Now, we see the formula. The energy supplied to the circuit by the source in time t is P into T. That is V into I into T. This energy is dissipated in the resistor as heat H. Therefore, H is equal to VIT. Very simple formula. Heat H is equal to V into I into T. Voltage into current into time. So we are applying the Ohm's law. R is equal to V by I is equal to V is equal to IR. We put V is equal to IR here. This becomes H is I square into RT. Okay. H is I square into RT. So we get two formulas for heat. Okay. This is called Joule's law of heating. It implies that the heat produced in resistor is directly proportional to the square of current for a given resistance, it's square of current, a resistance for a given current, and the time for which current flows through a resistor. In practical situations, when an electrical appliance is connected to a voltage source, H is I square RT is used after calculating the current using the relation I is equal to V by R. Okay, let's move ahead and try to solve a problem. The electric iron consumes energy at a rate of 840 volt when heating is at maximum rate and 360 volt when heating is at minimum. The voltage is fixed 220 volt. What are the current and the resistance in each case? Very simple. P is equal to VI, thus the current I is P by V. When heating is at maximum rate, I is equal to P by V. So what is P? Power 840 volt by voltage is 220 volt. That is 3.82 ampere. Resistance of electric current is R is V by I is 220 by 3.8 to 57.60 ohms. So when heating is at minimum rate, I is 360 watt by 220 volt, that is 1.64 ampere. Resistance of electric iron will be R is V by I. 220 by 1.64 is 134.15. These are all simple questions. You just have to remember the formula and apply it. That's it. You'll get the answer. Now, 100 joule of heat is produced. Heat is given in each second. Time is given 1 second. In a 4 ohm resistance, find the potential difference across resistor. V you have to find. So we have the heat formula. H is I square RT. We apply that. We get I. I square is H by RT ka square root. H is 100. R is 4. So 25 square root is 5 ampere. Thus the potential difference can be calculated by the Ohm's law, where R is V by I, so V is IR. We know I and we know R also 4. So 20 volt is the answer for this. Okay, V is 20 volt. Okay. Now we see some practical application of heating effect of electric current. What are the practical application? We all know an electric iron, due to the current passing through it, it's producing heat. We are able to iron our clothes. Same with the electric toaster. Electric current makes the heat. We are able to toast our toast. We have electric heaters, okay, working for us in cold conditions. We have electric kettles. We have electric oven, which works on the principle of electricity that produces heat. So for today, let's keep the session till here. I really hope it was useful and it added value to our learning. We'll see all of you in the next session. Thank you, everyone.